Recording has started, yeah. Maybe someone will have some idea what to do about them. So let's see. So, no, now the pointer doesn't work. I'm trying to advance. Oh, I have to do it here? No, I don't want to point. I want to advance the slide. It's not advancing. It was working. Oh, I think it was working before we. Oh, now it worked. What did you do?
I don't know. A stochastic process.
Can I do it on the computer? Up? Yeah, okay. Anyway, so I'm going to start with the Potts model. So this is probably something you all know, so I'll go quickly. You fix a finite graph, vertex set V and edge set E. Of course, in physics, we're interested in infinite lattices, but you do it by taking the limit of finite graphs. Fix an integer Q, which is the number of Potts states. You put a spin with values 1 through Q at each, you choose a value 1 through Q, that's this random variable at each side of the lattice. And the Hamiltonian is simply a delta function interaction. It only cares whether the spins at neighboring sites are same or different. And you can be either in the ferromagnetic case, J positive, or the antiferromagnetic case, J negative, or mixed, of course. And as you know, ferromagnetic Potts models have universality. Pretty much, you know, if I want to be the same as you and you want to be the same as Sergio and Sergio wants to be the same as Andrea, I mean, basically there are only two possibilities. Either that interaction is strong enough that you get ferromagnetic order, or it isn't and you get disorder. But antiferromagnetic cases are very different because being different from is not transitive, right? I want to be different from Sergio. Sergio wants to be different from Andrea. It matters whether I want to be different from Andrea or not. So it matters whether this is a square lattice or a triangular lattice or whatever. So anyway, so it was thinking about these questions that led me to think about working on general finite graphs and not just the usual regular lattices. And one way to start doing that is the Fortuin-Kasteleyn representation. Well, let me ask, are there any people here who speak Dutch? Because if so, I completely apologize for the way that I have mangled these two people's names. But anyway, so first of all, just note that the exponential of a delta function is just 1 plus a constant times a delta function. There are only two different energy states. And so the partition function is the sum over all spin assignments on the lattice, product over edges, and then this 1 plus V delta. And you expand out this product over the edges just by the distributive law. Let's let A be the set of edges for which the V delta term is taken. And now we fix the edge set A and perform the sum over the colorings. So that is, we interchange the sum over sigma and the sum over A. If you perform the sum over coloring sigma compatible with these constraints, what are these constraints? Each edge E that, so each edge in the set A imposes that the two spins at the ends of the edge have to be colored the same. So what that means is in each connected component of the subgraph VA, the color must be constant. And there are no other constraints. So you simply get Q to the number of connected components. Is there some way to turn off that stuff at the bottom that's covering up the bottom of the slide? Thank you. Perfect. So you simply get a factor Q to the number of connected components in the subgraph A. So this is, you've turned a model where the random variables live on the sites and take values 1 through Q into a model where the random variables live on the bonds and simply take the values occupied or unoccupied. And of course, the important thing is this is now a polynomial in the Q's, in Q and in all the V's. And so it gives you a continuation to non-integer values of Q. And so, for example, if you set all the v's to be -1, that says that nearest neighbors must be colored differently. Well, that's exactly the famous problem of proper Q colorings. And this gives the proof that the number of proper Q colorings, which is initially defined for positive integer Q, is actually a polynomial in Q, namely the chromatic polynomial. So that's interesting. And also there's several interesting limits as Q goes to 0. For example, if you take Q goes to 0 with the V's fixed, then you pick up these sets A that minimize the number of connected components. Well, the minimum number of connected components is 1. Namely, you connect up the whole graph. So you pull out one factor of Q and you get the generating polynomial of connected graphs. So that's a very interesting thing that graph theorists would be interested in. On the other hand, if you scale the V's proportional to Q and then let Q go to 0, a very simple calculation shows that you pick up the subgraphs that have the minimum number of cycles. Well, the minimum number of cycles is 0. Those are the spanning forests, the graphs that don't have any cycles. And you get the generating polynomial of spanning forests. And then if you let V go to a power Q to the alpha with anything in between those two cases, alpha equals 0 and alpha equals 1, then you pick up the graphs that have both one component and no cycles. And those are the spanning trees, which of course play an important role in electrical circuit theory, going back to Kirchhoff. So all sorts of interesting graph theoretical things come out as Q goes to 0 limits of the Potts model. Okay, so then you can think about different graphs and well, there are lots of interesting things you can do with the Potts model and the Fortuin-Kasteleyn random cluster model. But one thing that I thought to do was, okay, look at a very simple non-trivial case, the complete graph Kn, and I'm going to focus on the generating polynomial of spanning subgraphs, the one you get by the Q goes to 0 limit. So let Cn of V be the generating polynomial of connected graphs on n labeled vertices with the weight V for each edge. Okay, so you just count all the ways that you can choose the edges so that you make a connected graph. So this, of course, is something that graph theorists have looked at for a long time, but they didn't usually look at the generating polynomial. They would usually just count the number of connected graphs, Cn of 1. And one thing that my experience as a statistical mechanician has led me to think is there may be special values of the parameters like V that are important, for example, phase transition points, but there's no a priori reason to believe that those are at V equals 1. Right? So you study the polynomial for arbitrary values, and then you see where do you get interesting phenomena. Okay, so how do you compute Cn of V? Well, to actually write formulas for Cn of V, it's not easy. No one knows any closed form formula for Cn of V. But what you can do is get a closed form formula for the exponential generating function. So here's the idea. First, let's look at the generating polynomial of all graphs on n labeled vertices with a weight V for each edge. That's the Potts model at Q equals 1. But that's trivial. If you want all graphs, each edge is independently either occupied or not occupied. You either get a 1 if it's not occupied and a V if it's occupied. So you get a 1 plus V times raised to the power of the number of edges, which is n choose 2. So that's the total number, that's the total generating polynomial for all graphs. And then you form the exponential generating functions and use the exponential formula from enumerative combinatorics. Now, this is an interesting story. The exponential formula, which is a crucial formula in enumerative combinatorics, it was invented by statistical physicists in the 1950s. And the mathematicians do recognize that. They give the correct references. Of course, now it's been developed a lot by the combinatorialists. But what it says is the exponential generating function of the connected graphs is just the logarithm of the exponential generating function of all graphs. And what is the exponential generating function of all graphs? Well, we know it. It's x to the n over n factorial, that's the exponential weights, and then 1 plus v to the n choose 2. And so I'll write it this way. I'll define what I call the deformed exponential function, x to the n over n factorial, y to the n choose 2. And so you take the deformed exponential function, evaluate it at y equals 1 plus v, and take its logarithm. Okay. And more generally, if you care about the Potts model on the complete graph, its exponential generating function is just the f raised to the power q. Okay, now I should say, usually these formulas are considered as formal power series because if v is positive, if you're in the ferromagnetic case, then y is bigger than 1, and this series has 0 radius of convergence. But the series are convergent if 1 plus v is less than or equal to 1 in magnitude. So that's what you could call the complex antiferromagnetic regime. So in the antiferromagnetic regime, these are real sensible analytic formulas. Okay, so let me develop a few of the properties of this deformed exponential function. I mean, I think it should be considered one of the standard special functions, but it hasn't been studied a whole lot by mathematicians. A little bit, but not a lot. Okay, so one case is easy. If y is 0, then you have 1 plus x. That's going to be very important in what follows. If y is between 0 and 1 in magnitude, then it's easy to see this series converges for all x because y to the n choose 2 decays very fast. So it's an entire function of order 0. Order 0 means that the growth is very slow. It grows slower than e to the x to the alpha for any positive alpha. And it's a non-polynomial entire function. And then Hadamard tells you that it has a factorization of this kind. So it basically factors like a polynomial. A polynomial factors in terms of its roots. This factors in terms of its roots, except there are infinitely many roots rather than finitely many. For y equals 1, it is the exponential function. If y is on the unit circle but not 1, then it's an entire function of order 1 and type 1, which means it has a Hadamard factorization with some subtractions. It has a higher order Hadamard factorization. I'm going to focus on the case y between 0 and 1. And finally, as I said, if y is bigger in magnitude than 1, then it just has 0 radius of convergence, and it's meaningless. Okay. So what are the consequences of this for the generating polynomial of the connected graphs? So let's make, as I did, the change of variables y equals 1 plus v. So I will define c bar n of y to be cn of y minus 1. And then for y less than 1 in magnitude, you have this exponential generating function. And then, so you have log of the deformed exponential function. I put in the product formula for the deformed exponential function in terms of its roots. So I get a sum over k log of 1 over 1 minus x over a root. And then you extract the coefficient of x to the n from that, from the right-hand side, and you get an explicit formula for the generating polynomial of connected graphs. It's an extremely surprising formula. The left-hand side is a polynomial in n, polynomial in y, of degree n choose 2. The right-hand side is a total mess. These x k of y, we don't know what they are. They're certainly not polynomials. They're at most analytic functions of y. And we put them all together and we get a polynomial in y. Very surprising, but it's true. This is a convergent expansion for c bar n of y for y in the unit disk. And in particular, it gives the large n asymptotic behavior. Whenever the deformed exponential function has a unique root of smallest modulus, that root dominates the sum for large n, and you get this behavior. And so one question will be, when does it have a unique root of smallest modulus? So what can we say about these roots, x sub k of y? Well, for small y, we know at y equals 0, it's 1 plus x. So at small y, it's 1 plus x plus a correction. So of course, 1 plus x has a root. namely -1. So at small y, there ought to be a root which is -1 plus corrections. And this ought to be a convergent expansion. You can compute it. You know, it's a kind of perturbation theory. It should be a convergent perturbation theory. It is. There's an easy proof using Rouché's theorem that at least for y less than this number, this series converges. And more generally, you can get all of the roots. You have to scale them as they scale like y to the minus k. The kth root scales like y to the minus k. So you write x equals c y to the minus k, plug it in to the series, and now you see that the sum is dominated not by the terms k equals 0, n equals 0 and n equals 1. It's dominated by the terms n equals k and n equals k plus 1. And you can, again, read off that the root will be the thing coming from those two terms, which is minus k plus 1 y to the minus k, and then corrections. And you can make, for a slightly smaller disk of y, you can make this Rouché argument uniformly in k. So at least for y less than this number, something like 0.2, all the roots are simple, and they're given by these convergent expansions xk of y. And then I ask, might it be true that these series actually converge in the whole unit disk? Well, there are two ways that that could fail. There are two ways that, of course, they converge up to the first singularity. And there are two ways that a root could fail to be analytic, could have a singularity. One possibility is that two roots collide. And when two roots collide, you get a square root branch point. Second possibility is a root escapes to infinity. And there's a theorem of Alex Eremenko, unpublished, but in an email to me, where he proves that no root can escape to infinity in the open unit disk, except, of course, at y equals 0. At y equals 0, all the roots, except for the leading root, do escape to infinity. They escape like y to the minus k. But everywhere else, no root can escape to infinity in the open unit disk. And so I make the big conjecture that the other problem can't happen. Roots cannot collide. I conjecture that in the unit disk, all the roots are simple. If you buy that big conjecture, you combine it with Eremenko's theorem, and you get that each root is analytic in the whole unit disk. Okay, so that's, what I'm going to do is pile on one conjecture after another. I will eventually show that some of these conjectures are related, that some of the later conjectures imply the earlier ones. But these are all conjectures. None of this is proven. Okay, but I conjecture more. Not just are the roots simple, so they don't collide, they actually don't collide in modulus. They stay non-crossing in modulus. Right? The smallest root stays below the second root, stays below the third root. And it actually follows from that not only are they separated in modulus, they're separated in modulus by a factor at least absolute value of y. That follows by applying the Schwartz lemma to the ratios. Okay, and then what's a consequence of this, going back to the connected graph generating polynomials? So you recall the convergent formula. You use a variant of the Baraha-Kahan-Weiss theorem, which basically says that if there is a unique root of smallest modulus, then the C bar n of y doesn't vanish. And so the limit, the other way of saying it is the limit points of zeros of these C bar n's are the values for which the zero of smallest modulus is non-unique. But my hypothesis, conjecture 2, in fact, a weak form of conjecture 2 says that there's a unique zero of smallest modulus everywhere in the unit disk. So that means if that's true, the zeros of C bar n don't accumulate as n goes to infinity anywhere in the open unit disk. They, as n goes to infinity, run to the boundary. But actually, I think that more is true. I've computed them up to about n equals 80. I believe that for each n, these polynomials have no zeros at all in the open unit disk. Not just a question of n goes to infinity. At fixed n, they don't have any zeros in the open unit disk. In fact, I believe they don't have any zeros in the closed unit disk, except at the point y equals 1, where they do have zeros. So that's my big conjecture 3. And then you can ask, okay, I can pile on conjectures, but what's the evidence for these conjectures? So evidence number 1 is the behavior at real y between 0 and 1. And there's a theorem of Laguerre. When y is between 0 and 1, all the roots of this deformed exponential function are simple and negative real. So that's nice to know. And so a corollary of that is each root is analytic in a complex neighborhood of the interval 0, 1. Right? So you have at least a little complex neighborhood of the interval 0, 1. For each k separately, at least, there's a little complex neighborhood of 0, 1 where it doesn't collide with any other root. And now I want to combine this with evidence from numerical computation of these series. So I let, this was 13 or 14 years ago, I think. I let Mathematica run for a weekend to compute the series for the leading root. So there it is. Well, they're the first 14 terms anyway. Do you see any pattern in them? Well, not much, except, well, obviously they're rational numbers that you could have predicted. What you maybe weren't going to predict is they're all positive. And up to order 899, I verified they're positive. Later, I found a better algorithm. I computed it up to that order, I think it's 2 to the 16th minus 1. Anyway, I computed it up to that order. The positivity still holds. Okay. So I really think those coefficients are positive. I have no idea how to prove it. I also have shorter series for the higher roots. And again, the coefficients are positive. So big conjecture number 4, all of these series have non-negative coefficients. Now, combine that with the known analyticity. Do you remember Pringsheim's theorem from complex analysis? It says, if you have a power series with non-negative coefficients, then and it has a certain radius of convergence, R, then there is a singularity at the point R on the positive real axis. A series with non-negative coefficients, its first singularity is at least on the positive real axis. There might be others on the same circle, but at least there's one on the positive real axis. We know from Laguerre that there is no singularity in the interval 0 to 1. So up to not including 1. So therefore, Pringsheim, together with this non-negativity, if the non-negativity is true, implies that each root is analytic in the open unit disk. So that was my first question. Could it be true? And the answer is yes, it sure looks like it's true, modulo this non-negativity that I don't know how to prove. That I have no idea how to prove, let's put it that way. But more is true. Let's look at the reciprocal. The reciprocal, 1 minus blah. Do you notice something about that series? Well, one thing you notice is these rational numbers look a little bit simpler than those, which might be telling us something. But I think the other thing to notice is all of the coefficients after the constant term 1 are negative. That implies the previous thing, right? If you take a series 1 minus blah, and take its reciprocal, you get 1 plus blah. The converse is not true. So this is stronger than what I just saw. So big conjecture number 5, if you look at the reciprocals, they have all non-positive coefficients after the constant term 1. That implies the previous conjecture, but stronger. But now look at this. As y goes to 1, the deformed exponential functions approach the ordinary exponential function, e to the x. E to the x has no roots. So what happens to the roots of the deformed exponential function as y goes up to 1? They have to march off to infinity. So that's a theorem. It's easy to prove that, and notice also, remember, Laguerre says they're negative real. So these xk of y's are going to minus infinity as y goes up to 1. that means their reciprocals are going to 0. I have a series, 1 minus blah, and at y equals 1, this makes 0. It means all these coefficients blah have to add up to 1. Now, I don't know, what do you call a series of non-negative numbers that add up to 1? I call it a probability measure, right? So if this big conjecture 5 is true, for each k, all the coefficients after the constant term 1 in this reciprocal series are the probabilities for some positive integer valued random variable. What on earth could that random variable be? I have no idea. Well, you saw what they were, at least for the leading root. Try to invent a natural random variable that has those probabilities. But I conjecture that even more is true. So let's look at these c bar n of y's. And I'm just rescaling it to make it a polynomial with constant term 1. And then recall that this leading root is, well, recall that the c bar n of y's are gotten by summing over the roots raised to the nth power. So if you take the 1 over n power of them, or the minus 1 over n power, you will recover the leading root. So the leading root is gotten by taking these dn of y's and raising them to the power minus 1 over n. And I conjecture that the positivities that we observe for the leading root are actually true, not just in the limit n goes to infinity, they're true for each n. So for each n, you take this c bar n of y, rescale it, and raise it to the power minus 1 over n. I believe it has all non-negative coefficients. It's a power series now. It's a polynomial raised to a fractional power, and I believe that it has all non-negative coefficients. And even more strongly, if you take dn of y raised to the power plus 1 over n, it should have all non-positive coefficients after the constant term 1. And what does that mean? Dn of y is positive for y between 0 and 1. That's easy to see. And the only way that raising it to a power can have a singularity is if you have a 0, but you don't have a 0 in the interval 0, 1. So Pringsheim would imply that big conjecture 6a implies big conjecture 3. That is, there are no zeros in the unit disk. And secondly, big conjecture 6b implies that for each n, those coefficients are the probabilities of a positive integer valued random variable. So the one you saw a few slides back was the random variable for n goes to infinity, but you can do this for any n. Do it for n equals 2. Well, it's easy to do the calculation for n equals 2. Do it for n equals 3. It takes a little more work. Even for n equals 3, with a little bit of work, I can prove that 1 minus d3 to the 1/3, those coefficients all do have the claimed sign. So I can prove big conjecture 6 for n equals 2 and n equals 3. And I believe I have a method that with more work and computer assistance can prove it, with more work for more n's. And maybe I can go up to about n equals 20, but that's all. And I have no idea what these random variables are. I mean, presumably it has something to do with some kind of combinatorial or probabilistic process on the complete graph with n vertices, but I have no idea what it is. But in any case, these random variables for finite n would generalize the ones for infinite n in roughly the same way that the binomial generalizes the Poisson. Okay. And all of this is actually just a special case of a much wider framework. You can look at power series, just take any power series you like, an x to the n, and put on this y to the n choose 2, and play the same game looking for the roots as power series in y. And so you can do it for the deformed exponential function, as I've been doing. You can do it for the partial theta function, which is the same function, but without the n factorial. You can do it for this Q deformed exponential generating function, Q deformed exponential function, which interpolates between the partial theta function and the deformed exponential function. And more generally, you can make deformed hypergeometric and deformed Q hypergeometric series. And in fairly wide examples of these deformed hypergeometric series, I found empirically that conjectures like the ones I've shown you are true. Again, no proofs. The only case where I have proofs is for the partial theta function, where I was able to use Q series identities to prove the positivities. But other than that, it's a huge open area. I have not made any progress on it, and I hope someone else will. So you can look, if you're intrigued, you can look at some lectures I gave at Queen Mary in London, so 11 years ago now. And the one proof I have is this one on the partial theta function. Okay, so that ends the first half or first part of my random walk away from statistical physics. Here's the second part. But again, it's starting from the same object, namely the generating polynomial of connected graphs. Okay, so start from this generating polynomial of connected graphs. Of course, the smallest connected graph are the spanning trees. So you have n-1 edges, and there are n to the n-2 of those. The biggest connected graph is the complete graph itself. There's one, and it gets weight v to the n choose 2, and then you have all that stuff in between. So I want to pull out the factor v to the n-1 and make the change of variables that we did before. And so I'll just pull out that factor and define in of y like this. It's obviously a polynomial in y because the factor I pulled out was there. It's a polynomial of degree n-1 choose 2. Its value at 1 is n to the n-2. Its value at 0, it's not hard to show, is n-1 factorial. What's a little bit surprising, perhaps, is that it has non-negative coefficients, and that's because it counts something. What does it count? It counts trees. It's the so-called inversion enumerator for trees. And what do I mean by that? I consider trees on the vertex set 1 through n. I consider them to be rooted at 1, so 1 is forced to be the root. And then I look at it as a rooted tree. And an inversion is a pair I greater than j, such that I is an ancestor of j, right? It's kind of out of order, right? It's an ancestor, but it's higher numbered. That's an inversion. And in of y counts these trees with a weight y for each inversion. The proof of that is not difficult. It's a kind of interesting combinatorial argument that has to do with partitionability of complexes. And well, it goes back to combinatorialists, but actually was kind of foreshadowed in the work of the statistical physicist Oliver Penrose, who is the brother of the more famous Roger Penrose. So in an article that Penrose wrote in 1970 concerning the cluster expansion in statistical mechanics, he has things related to this. Even more surprisingly, if you look at the coefficients of this polynomial, they're log concave. That is, the logarithms of them form a concave function of n. That's a little bit more of a surprise. I had discovered it empirically, and I didn't know what to make of it. It turns out it's a special case of a deep result of Jun He from 10 years ago, where he proved the log concavity of the H vector of the independent set complex of any matroid representable over a field of characteristic 0. Doesn't matter if you know what that is. I've forgotten what most of those words mean. But anyway, you apply it to one particular matroid, namely the cographic matroid of the complete graph Kn, and you get this log concavity of the coefficients of in of y. I once asked her, do you know any proof for this special case that's any simpler than proving it for all matroids? And he said, no. A little bit embarrassing. But anyway, he got the Fields Medal a few months ago for this. Not bad work. And it's an open, there really ought to be a more elementary proof for IN of Y. I mean, there's no hope for me to try to read his proof. I mean, he uses algebraic geometry to invent some things that, I don't know, some homology groups count. I have no idea. But anyway, there ought to be, for this particular case, some kind of elementary combinatorial proof. Okay, I'm not going to talk about that log concavity. I'm going to talk about a different kind of mysterious positivity. And it's motivated by the Stieltjes moment representation for this IN of Y. So again, recall that these connected, the generating polynomial of connected graphs has this representation as moments involving these unknown roots of the deformed exponential function. And then you put in what is IN of Y, and that tells you that IN of Y has a moment representation like that. Now remember Laguerre. Laguerre says that when Y is between 0 and 1, the roots x sub k of Y are real and negative. So if x sub k of Y is real and negative, and Y is between 0 and 1, all that stuff in square brackets, oops, yeah, all that stuff in square brackets is positive. And minus xk of Y, the weight, is also positive. So this is a Stieltjes moment representation. That is to say, it's writing IN of Y as the moments of a positive measure on the positive real axis. In this case, it's a discrete measure concentrated at discrete points. But anyway, it's a measure. And in fact, I will replace n by n plus 1. So IN plus 1 of Y, and I divide by the n factorial. That's a Stieltjes moment sequence. On the other hand, n factorial is a Stieltjes moment sequence. It's just moments of the exponential. And it's easy to show that the product of two Stieltjes moment sequences is also 1. So therefore, for each Y between 0 and 1, this sequence of the inversion enumerator for trees is a Stieltjes moment sequence. Okay, what am I going to do with that? I'm going to relate it to a kind of bizarre concept called total positivity. So a matrix, finite or infinite matrix of real numbers, is called totally positive if all its minors, 5 minutes? Yeah, okay, I think I'll make it. Yeah, it's called totally positive if all its minors are non-negative. And I stress all its minors, not just its principal minors. So this is not like positive semi-definiteness. It's all the minors. I take any subset of rows, any subset of columns of the same cardinality. That submatrix has to have a non-negative determinant. That's what totally positive means. It has applications to millions of different things. And I just want to focus on this theorem that relates it to the Stieltjes moment property. A sequence of real numbers is a Stieltjes moment sequence if and only if its Hankel matrix is totally positive. So the Hankel matrix is the matrix whose anti-diagonals are constant, A sub I plus J. And so the application from what we just saw, this is a theorem, right? For Y between 0 and 1, the Hankel matrix of the inversion enumerator for trees is totally positive. Otherwise put, look at the minors of this Hankel matrix. The entries are polynomials in Y, so the minors are polynomials in Y, and each one of these minors is a polynomial in Y that's non-negative between 0 and 1. Okay. Well, so I decided to compute these minors. So I think I computed up to the 10 by 10 Hankel matrix. It's, you know, these things get big because the IN of Y has a degree n choose 2. So these things get very big, but I did compute, well, I didn't. My computer computed up to 10 by 10. They're polynomials in Y. We know that they're going to be non-negative on 0, 1. Maybe you won't be surprised that they're actually non-negative on the whole positive real axis from 0 to infinity. That might not surprise you, but here's the surprise. They are polynomials in Y with non-negative coefficients. That's a lot stronger than pointwise non-negativity. So I call this phenomenon coefficient-wise Hankel-total positivity. It implies Hankel-total positivity for all non-negative y, but it's much stronger, right? I mean, there are lots of polynomials that are non-negative on the positive real axis, but are not coefficient-wise non-negative, like 1 minus 2y plus y squared, right? So unfortunately, I have no proof, not even for the 2×2 minors. The 2×2 Hankel minors are just these log convexity quantities. So just look at that quantity. That ought to be coefficient-wise non-negative, and there ought to be some kind of combinatorial proof of that, but I have no idea how to do it. But coefficient-wise Hankel-total positivity seems to be actually a frequent phenomenon in enumerative combinatorics. Lots of generating polynomials for interesting combinatorial objects seem, empirically at least, and in some cases provably, to be coefficient-wise Hankel-totally positive. For example, the Stirling cycle polynomials, they count permutations by number of cycles, a weight x per cycle. Or the Eulerian polynomials, they count permutations by number of descents. Or the Bell polynomials, they count partitions of an n-element set into non-empty blocks by the number of blocks. Or the Narayana polynomials, they count non-crossing set partitions, or many, many other things. And you can make multivariate generalizations where you look at several different statistics and you introduce several different variables conjugate to them. There are many, many cases where coefficient-wise Hankel-total positivity seems to be true. And in some cases, there are now proofs. But alas, not for the case that started it all. I find this embarrassing. The place where I first discovered the phenomenon of coefficient-wise Hankel-total positivity was In of y. This now seems to be one of the cases that I understand the least. Okay, so it would be another talk to explain all this, but there are connections with continued fractions. It goes back to Euler, Stieltjes, Ramanujan, especially work of Flageolet in 1980. It connects with orthogonal polynomials and multiple orthogonal polynomials, which is something relatively new. There's a combinatorial concept called production matrices that turn out to be a very important technical tool. Reardon arrays, another one. There may be connections with non-commutative probability and a lot of other things. So I gave an overview of this a few years ago at the Orthogonal Polynomials and Special Functions conference. There's a paper that Matthias Pétriol and Bertrand Joux and I wrote on the relation between this stuff and continued fractions, where we take the work of Euler and Stieltjes and Gauss on continued fractions, and we generalize it to something that we call branched continued fractions. And finally, there's what was going to be a paper, but ended up getting a little bit too big. So it will have to be a monograph to be finished someday, hopefully in time for Sergio's 80th. So thank you all, and tanti auguri Sergio. Questo è Serena, quando aveva un po' meno di 2 anni. She's 16 years old now. And there is Sergio with some uneaten food, but very happy behind his Mac. So thank you all.
Thank you for this interesting talk. Two also in complex analysis and difficult conjectures will still have to be proven. And then,
but probably less difficult than those of the talk before lunch, I hope.
So I found this very entertaining, but I have no idea what it has to do with any problem in the real world that I would like to know the solution of. But what are the applications of all these miraculous properties?
None, as far as I know. I don't know. I mean, I just find it miraculous that things that, you know, ought to be rational numbers of both signs end up being non-negative. And it means something. And as I say, I believe the phenomenon goes beyond just the deformed exponential function, because I've found versions of it for deformed hypergeometric functions. So I don't know what it means. But, you know, sometimes with these things, you don't know what the applications are, right? Dick Askey and who was it? Gasper proved this inequality for, I can't even remember which polynomials, whether it was Jacobi polynomials, that, you know, no one thought was of any importance until de Branche used it in his proof of the Bieberbach conjecture. So, you know, these things, you have no idea what something is good for. Maybe it will never be good for anything, but maybe it will turn out to have some unexpected application.
So now these coefficients, you know them up to order 16,000 or something like this.
Yeah.
So did you try factorizing them over the primes to see if
Yes, I must have. I mean, they don't look anything simple. But even with my coefficient-wise Hankel-total positivity conjectures or Stieltjes moment conjectures, one thing you can do with any Stieltjes moment sequence, Stieltjes proved that a sequence of real numbers is a Stieltjes moment sequence if and only if you can write it as a continued fraction of a certain form with positive coefficients. So I have a program, MATHEMATICA program. You give me a sequence, I'll compute its continued fraction coefficients. So again, there are lots of cases where I've computed 2,000 of these continued fraction coefficients. They're positive rational numbers, but I can make no sense of them. So of course, one thing I do is I look for the prime factors. And most of the time there's something ugly. And then, of course, if there's something ugly, it doesn't mean that there's no logic behind it. It just means that the logic behind it is not purely multiplicative, right? It could be additive and multiplicative.
I mean, people who have worked on combinatorial properties of wave functions in quantum systems and quantum Kniesnik-Samologikov stuff, they routinely seem to be able to conjecture things out of series that have only 10 terms. So, I mean, there should be some hope here.
Yeah, I would be glad to share with you or with anybody my 16,000 terms. I warn you that of the last, each term is something like 160 megabytes. But I'd be glad to dig them up and share them with anybody who wants them. As I said, at a certain point, I gave up because I had all these beautiful conjectures and I didn't know how to prove them. So I really hope that somebody will have a new idea.
Thank you. So let's thank the speaker again.